All right, to finish off, we were going to look at statistical inference, which is where we go and infer properties of a larger population using our sample. And so we assume that our sample has all the features of the overall population. So what is sampling? Is selecting a random set of elements from the greater population. Why do it? Well, it's quicker than going and surveying every single piece of data. It's certainly cheaper than doing that. And accuracy, strangely enough. When you draw data from large amounts of numbers, then there is a tendency to miscount and things like that. So it's actually more accurate to use a sample. Necessity. It's very hard to test for quality on every single item if you can end up destroying all those items. For instance, if you want to work out defective matches, well, if you were to strike every single match to see if they were defective, well, you'd have none left because you've destroyed all the good ones. How should these samples be drawn? Well, it's always randomly. Now, a sample is going to be random when every piece of the population has an equal chance of being selected. And that way there's no bias or predictability about our sample. So a random sample isn't necessarily a cross-section of the population. Remember, it's purely random. So some notation and terminology. How we're collecting our data. If we're gathering from the whole population, we call it a census. If it's just a sample, then we call it a survey. So probability x equals x. For population, we use px. For sample, we talk about relative frequency rather than probability. Expected value x is the mean. It's just that the notation for the mean is different. We use mu when we talk about a population, x with a bar on top if we're talking about the sample. And for variance, the difference is we use sigma in the population, we use s in the sample. Now, as n approaches infinity, so the more and more pieces of information we gather, then our sample average should approach the population average, and the same with the deviation. All right, let's have a look at this example here. We're going to roll 2 dice, and we're going to use theoretical probability to calculate the expected value and the variance for the population. If we were to use the population, then the probabilities for rolling the different sums I've recorded there. So the expected value would be 7, and our variance would be 5.83 repeater. So the standard deviation, 2.4152. And there's the graph, and you can see it's nice and symmetric. All right, we're now going to do a simulation where we roll 50, then 100, 500, and 1,000 to see how that compares. Here's my experiment where I did 50. I've got the population above it so we can compare. How close did I get? Well, for my random sample, I got an expected value of 6.42. And so the difference there, you'll notice, is 0.58. And my variance, 5.8036, which means the difference with the deviations are really close, actually, 0.0061. And there's the graph. So the asterisks are the experiment, and the diamonds are the actual probability. Okay, 100. 7.16, so a difference of 0.16. Variation, and then deviation, and our graph for that one. And you can see those asterisks are sort of coming in closer to the diamonds. All right, 500 times. 6.86 for the expected value, so I'm out by 0.14. Variation, 5.644. Deviation, 0.04. And there's my graph. Finally, if I did it 1,000 times, 7.042, so I'm only 0.042, and the deviation, 0.0619 difference. And now you can see, having done it 1,000 times, actually my sample is very, very close to the actual population results. All right, look, I'm only going to do 4 questions. It's out of 13D.